Okay, let's start the second talk. The second talk is given by Kun Fang, and he's going to tell us about the generalized quantum asymptotic equipartition and applications.
Okay, thanks very much for the kind introduction, and also welcome to this talk. So I'm Kun Fang. I'm currently, it doesn't show the slides on the big screen. Okay, so I'm currently working at the Chinese University of Hong Kong, Shenzhen, and this talk is about the asymptotic equipartition properties. So this is a mathematical properties that are widely used in information theory. So we give a significant generalization of these properties, and I will also show you a few applications of it. So this is a joint work with Hamza Fawzi, Omar Fawzi, and you can refer to these archive papers. Okay, so, to begin with, let's review what is asymptotic equipartition, right? So, or AEP for short. So you can think of this as a form of the law of large numbers in information theory. So suppose you have a sequence of IID random variables xi to x1 to xn. So the probability of these variables will converge to the entropy of the variables. So this is AEP. So this directly gives rise to the notion of typical set and non-typical set, right? So imagine that we are working with a bit string of length n. This is a set of bit strings of exponential size, but you can put your focus on the typical set in the red. So the good thing for this is that this typical set only occupies a small portion of the exponential large space, but it has almost all the weight on it. And more importantly, every element in the typical set are nearly equiprobable. So this really lies in the heart of information theory and give rise to a lot of applications such as data compression, channel coding, and cryptography tasks. So actually, the AEP can be written as a more generic form in divergences. So here we can consider two probability distributions, P and Q, and you can take the divergence of interest on the left-hand side. Then we can ask a question whether the left-hand side converge and where it converges to. And usually the left-hand side will converge to the K-error divergence or relative entropy in the classical setting. So we say this is a more generic form because if you think of the mean entropy and max entropy, you can reduce to the classical AEP I introduced in the previous slides. And also if you think of the hypothesis testing relative entropy, this will correspond to the well-known Chernoff-Steins lemma. So based on this more generic form, we can easily extend it to quantum setting, quantum AEP, by replacing the probability distribution with density operators. Right? Now you have two density matrices, rho and sigma, and on the left-hand side, you can replace your divergence with quantum divergences. And you ask the same question, whether this left-hand side converge and where it converges to. And typically, it will converge to the quantum relative entropy by omega key. So the notion of quantum AEP has been extensively studied in the community. For example, for hypothesis testing relative entropy, this corresponds to the quantum Steins lemma. And also for the conditional entropy and the Dmax, the AEP also holds. So because AEP is in the heart of information theory, and similarly here, quantum AEP also plays a crucial role in quantum information science and has applications like quantum data compression, quantum channel coding, quantum cryptography, and quantum resource theories. Okay. But there's a limitation on the existing quantum AEPs that we have here. It only works for singleton and IID structures. You only compare rho tensor n and sigma tensor n. But in the general case, right, what if the quantum state we have is a many-body quantum state, and each copy of it has correlations between them, and also sometimes you may not have a precise description of the states that we observe. You only know that the object is in a certain range of quantum states. So this has practical motivations in the classical setting. So you can refer to this paper and the reference therein. So the authors introduce a few practical applications, such as speech recognition, radar target detection. Those applications do require a more general notion of AEP in the classical setting. So this motivates us to study a more general quantum AEP beyond the IID and the singleton case. So here, imagine that you are comparing two sets of quantum states, AN and BN. And you can ask the same question whether the left-hand side of this equation converge and where it converges to. Right? So if you think of the divergence between quantum states as the distance of these two states, then the divergence between these two sets of quantum states are simply the minimum distance between these two sets. Okay, so this is really a very general framework that contains almost existing quantum AEPs in the literature, including the popular generalized quantum states lemma. So the generalized quantum states lemma is a special case here. The AN is just a row tensor n, and Vn is a set of quantum states. Okay, so this is related to the two plenary talks in the morning. So our answer is like this. So if you compare two sets of quantum states, the left-hand side indeed converge, and it will converge to the relative entropy of these two sets. On the right-hand side, you need to take the regularization because, in general, this quantity is not additive. Okay, and this is a really general result. So first of all, for divergence, it works for hypothesizing relative entropy and Dmax. So these two quantities serve as the two extreme cases in a bunch of divergences. So any divergence in between or equivalent to them will yield the same result. And also in terms of the sets, right? So the convergence does not come for free. So you need to assume a certain structural assumptions on the set you are interested. So the first three assumptions in blue are standard in the literature. So it's convex, compact, permutation invariant, and closed on the tensor product. So our work here introduced another assumption, 8.4, on the polar set of AN. So the polar set can be think of the dual picture of the set you are interested. Okay. So 8.4 is currently a pure technical assumptions, but it is indeed satisfied by a lot of cases of interest. For example, singleton, the channel image of a quantum channel, and also in the recovery setting, you have a fixed state. You range your all the quantum channels around it. This is studied in the recovery setting, and also the extension set. Right? You fix your marginal state. You consider all the possible extensions of this marginal state. This is useful in Ullmann's theorem, and also a bunch of sets in quantum resource theory. Also, if you aim to remove the technical assumption 8.4, the AEP will not hold in general. So you can find the counterexample in these two archive papers. And more importantly, right, so our results have a very good advantage over existing AEPs or states lemmas. It's about the efficiency. So the right-hand side is a regularized quantity. You need to take the limit n goes to infinity. But this regularized quantity in our setting can be indeed efficiently estimated. So we have explicitly lower and upper bounds, and these bounds will converge to the same thing. And we have an explicit convergence rate for this. So this gives rise an efficient approximation of the optimal rate by using quantum relative entropy program of polynomial size. And you can refer to this archive paper for more details. And besides the AEP we written in the box, actually we have a stronger result that gives you a finite n estimate. Okay, so we can estimate the left-hand side quantity up to the second order. So leading order is a regularized quantity, but in our case, we can still provide a second order estimation to make the convergence controllable. So this is a very real case in quantum information theory, and probably the only one that I know. Okay, of course, the second order is not the usual square root of n, so there's some potential improvement in the second order term. So the key technical tool we use is the superadditivity of measured relative entropy. So once we impose the polar assumption, we can prove that the measured relative entropy between these two sets is superadditive. So you can approximate the quantity d by using the measured relative entropy from below. And once you regularize it, it will converge to the thing that you want. And you can do the same thing for the upper bound by using the sandwich relative entropy of these two sets. Okay, so let's recap what we have doing here. So we know the AEP can be written as a more general notion of divergence. And based on this, we can easily extend it to the quantum case by replace the probability distribution with density operators. And in this work, we go even further that we compare two sets of quantum states beyond IID and singleton cases. Now you can compare two general sets of quantum states. Okay, now I'm going to show you a few applications. So due to the time limit, I'm going to focus more on the first two applications. Okay. So the first application is about hypothesis testing between two sets of quantum states. So suppose you have two sets, AN and BN, and the tester can draw samples from this set and make measurement to determine which set the samples belongs to. Okay, so in this case, you have two kinds of errors. The type 1 error say the sample actually from AN, but we classify it from BN. And also type 2 error, the sample is from BN, but you classify it as AN. Okay. So the goal is that we want to keep the type 1 error within a fixed threshold to control the false positive. Because, for example, in COVID-19, a healthy people get a positive test. This is not good news and will bring troubles to the guy. So we want to control this error probability within a certain threshold. And based on this, we optimize the type 2 error probability and observe the optimal behavior of this. So the answer is like this. So the optimal type 2 error probability will exponentially decay at a certain rate given by the relative entropy between these two sets. And of course, it will reduce to the classical Generalized lemma and also the quantum state lemma if you think of your set as a tensor product state. And also, we can compare it to the generalized quantum state lemma. So in generalized quantum state lemma, the AN is just a tensor product state. Okay, so the generalized state lemma got popular recently because the little story behind it. Okay, so so this initial idea was proposed by Brando and Planio 15 years ago and becomes the foundation for a lot of applications. And later, in 2021, my collaborator and I are trying to study the hypothesis testing or state lemma between two quantum channels. So, but it turns out that our result is wrong. So actually, so we borrow a technical lemma from Brando and Planio's paper, and it turns out that technical lemma is wrong. So this triggers the finding of the gap of the original proof. And later, a few experts in the community write a paper to formally point out this gap and study the consequences. Okay, but luckily, right? So later last year, we have two solutions to save the results. So one by Hayashi and Yamasaki, the other one is by Ludovico Lamy. So and in this work, we have a similar result, so we can compare it a little bit. So of these three results works under certain assumptions on the set we observe. So in particular, Ludovico Lamy's results make use of all the 5 assumptions from Brando and Planio in the original paper, but Masahito Hayashi and Yamasaki's technique can only use a subset of the assumptions and give a stronger result. So our case here propose the assumption on a polar set, but we do not need the assumption 5 and assumption 6. So in summary, so our result here is not directly comparable to the previous generalized quantum state lemma. It is weaker in the sense that we impose the polar assumption for the second set, but it is stronger at least in 2 aspects. The first one is that we allow composite hypothesis in the first argument, and also more importantly, our result is efficient computable for the optimal exponent. So this addressed the open problem by Brando and Amharo in one of the paper, and the other one by Mosoin. So the efficient computability really set apart our result with the existing state lemma. Okay, so the one of the most important application for generalized state lemma is to help us to have a better understanding of the reversibility or the second law of quantum entanglement. So in the standard resource manipulation, so we aim to transform rho tensor n to sigma tensor n. If you can transform sigma back to rho without any loss, then we say the resource series is reversible. And now, based on our generalized AEP, you can do the same thing on almost the same framework for 2 sets of quantum states. You transform a set of quantum states to another set, and now you can transform it back without any loss. And this is the optimal rate transformation in the box. Okay, the second application is about the adversarial channel discrimination. So in this setting here, we have a black box, untrusted box. untrusted devices that can generate quantum states upon request. And as a tester, he can request samples and perform measurement to make a guess whether the box behaves like N, or the bad case, or channel M, the good case. So the tricky thing here is that this is a black box. It's untrusted, so it plays the role as the adversary. So the adversary may possess environmental system of the channel, and it may also have internal memory to correlate with the generated samples to mislead the tester's ability to identify the channel. And the question here is, how efficiently can the tester distinguish between the two cases, bad case or good case, while playing against the adversary? So the classical setting has been studied by Brandel and Aaron Harrow in this paper, and now we give a fully quantum generalization. So because as a tester, the box is complete black. So as a tester, he don't know what the adversary perform inside the box. So the quantum states that the tester obtained only in a certain range of the set, AN or BN, depending on the device, how the device behaves. And the adversary can perform adaptive strategies to manipulate the environmental system of the channel and also do update operations between each state generation. And the other more simpler strategy is non-adaptive ones. The adversary do nothing on the environmental system and do not do any update in the middle of the generation runs. So our answer for the optimal performance of the tester is like this. No matter the adversary perform adaptive strategies or non-adaptive strategies, they give the same result. The optimal type 2 error both converge to the minimum output entropy of the channel of these channels. So this is a new notion for channel divergence. We call it minimum output channel divergence, similar to the minimum output entropy. So this is essentially the minimum divergence of all the output state between the two channels. So the message here is that adaptive strategies offers no advantage over non-adaptive ones in this adversarial channel discrimination. So this is the good news for the tester, because no matter how the adversary behaves, we know the worst case rate. Okay, the key technical tool we use is these chain rule properties for measure relative entropy and also the sandwich relative entropy. Okay, so the third application is the relative entropy accumulation theorem. So entropy accumulation studies how the entropy accumulates when we perform a sequential operations on the quantum state. Right? So we want to know how the optimal, how the entropy of the last system behaves. So this has widely used in quantum cryptography tasks. So then there's an open question asked whether we can generalize the existing entropy accumulation theorem for conditional entropy to relative entropy. So if you can do this, then we will have more applications, mostly in cryptography tasks. So here, by using our AEP, we can give an answer for hypothesis testing relative entropy. So you can see in the box, the entropy of the final stage actually come from the entropy of each round of your operations. So let's say the entropy accumulates once you perform a sequential operations on it. And also, we have applications in quantum resource theory. So sometimes the technical assumption on the polar set is not directly satisfied, but we can do relaxation, right? So, for example, the set of separable states does not satisfy the polar assumption, but we can relax it to the range set. And then this will help us to give an efficient approximation of the relative entropy of entanglement from below. And we can do the same thing for the resource theory of magic, that you relax the set of stabilizer operations to the set of non-positive mana. Okay. So using these ideas, we can have some quantitative improvements for a few tasks, entanglement cost of quantum state and channels, entanglement distillation, magic state distillation, and we believe we should have more applications. But yes, you can refer to this archive paper for more details. Okay, so this is a brief summary of the talk. So we have given a significant generalized quantum AEP. Now you can compare two sets of quantum states with correlations and beyond IID and singleton framework under certain structural assumptions of the set. And there's a good advantage of this AEP is that even though it's a regularized quantity, you can still efficiently approximate it. And the technical tool we use is the superadditivity and chain rule probabilities. So these are two new technical tools that we hope can be useful in your own research in the future. So because AEP realized in the heart of information theory, so we do expect to have further studies and more applications on it. And actually, there's already a recent paper make use of our results in quantum cryptography tasks. Okay, this will be the last slide. So I'm now working in the Chinese University of Hong Kong, Shenzhen. So this is a very confusing name because it has 3 locations. But it's actually, the campus is actually in Shenzhen, next to Hong Kong, inside China. Okay. Yeah, so people call it, so Shenzhen is a very nice city. People call it California in China, so it has very nice weather. I'm now looking for postdocs, PhD, research assistants. So if you're interested, you can talk to me or drop me an email. And also, of course, in our school, we also have faculty positions open, so you can talk to me for further information. Okay, so thank you very much for your attention.
Thank you for the nice talk. In question, we just have one question. Yep.
Hi, thanks for the nice talk. I was curious because some time ago we had a result on proving an asymptotic equipartition property for ergodic states and translation invariant states. So I was wondering to which extent you can generalize your generalized asymptotic equipartition theorems to translation invariance rather than permutation invariance.
Yeah, it's possible. The only technical difficulty we have here is we want to have a approximation of the relative entropy from below. So here we utilize the measured relative entropy to approximate it. And we hope that this quantity is super additive. So because once you regularize it, it will converge to the thing that you want. That's why we impose the polar assumption. So in our case, in your case, if you want to have a more extensions, you need to go in this direction to see whether the setting you have is super additive for measured relative entropy.
We can take one more question.
Hey, thanks for the nice talk. Right, so first of all, like an observation, so like, I mean, it's true that in my approach, you use all of the 5 axioms, but the reward for that is that you get a stronger statement. You get this beyond IID type of statements that also work when the first argument is not exactly IID.
Yes.
So that's what you gain. So in this sense, it's you get something more. Okay, so and as for the questions, so do I understand correctly that basically you have an algorithm to approximate the regularized relative entropy to the range set?
Yes, exactly. So the algorithm actually works for all sets that satisfy the 4 assumptions.
Yeah, okay. So for entanglement theory, this would be the most natural candidate range set, I guess, right?
Yes. So which means now regularized range information can be efficiently computed.
Do you know if that can be smaller than the regularized relative entropy of NPT-ness? So like, did you look at this? And now that you have this computational tool, you could actually try to find gaps between this and other measures, right?
Yes, that's a good point. Yeah, it's worth to try to structure, but I haven't tried it. Yes.
Yeah, do try. I think it's interesting.
Thanks.
Okay, let's thank the speaker again.